Welcome everyone. In this video, we are moving into data visualization. Up to now, we've been focused on infrastructure, how data is modeled, how it's stored, how it's queried. All of that work is necessary, but none of this directly supports a decision until a human can understand it. And that's exactly where data visualization comes in. So let's get started. Here's our roadmap for this video. First, I will place visualization inside the data triad, so we will see why it matters. Then we'll talk about the power of visualization, why visuals can change how humans think. After that, we will talk about what data actually goes into visualization and how we talk about it precisely. And finally, we will walk through several different types of visualization and more importantly, what kinds of questions each one is good at answering. So let's bring back the data triad. You'll remember this framework from earlier in this course. At the bottom, we have data collection and data storage. And then in the middle, we have data management and processing. And then at the top, we have the use of the data for decision support. So visualization sits squarely at the top. And that's the point where data stops being an IT asset and start becoming a managerial asset. So I like to make a cooking analogy here. So think of your data warehouse as a professional kitchen. You've sourced high quality ingredients. They're cleaned, chopped, and stored properly. Everything is labeled and organized. But then the visualization is the cooking and the plating. And decision making is a diner's experience. You can have the best ingredient in the world, but if the plate is confusing, cluttered, or ugly, the diner won't trust the food. So now let's move to the heart of why visualization matters. So first of all, what exactly is data visualization? So formally, data visualization is defined as graphical representation of data using visual elements, lines, points, rectangles, circles, and these are supposed to support and enhance human cognition. And that sounds a little bit abstract, so let's translate it. So visualization is about using our eyes to do work that our brain is bad at. Humans are terrible at scanning tables of numbers and comparing values. But humans are incredibly good at noticing differences in length, position, and colors. Visualization will take advantage of that biological fact. It's not about changing the data. It's about cognitive efficiency. So in visualization, we almost never visualize raw data directly. Instead, we aggregate data first. We sum, we average, we count, and then we encode those aggregated values into visual elements and what we call those as marks. So you can think of this as compression. The aggregated values are then encoded into the attributes of our marks. So let me show you what I mean with some examples here. Look at the bar chart example. Each bar represents a region: west, east, central, and south. The length of each bar encodes the total sales for that region. Longer bars means more sales. Shorter bars means less sales. So you can notice something very important here. We don't need to read a single number to know which region performed the best. Our visual system answers that question instantly. So most visualization places marks on coordinate plane. So X and Y axis, and this will help to encode values precisely. But precision is not always the goal. A pie chart, for example, doesn't need axes. So here, the angle or the arc of each slice represent the percentage of internet usage by continents back in 2012. The visual proportion tells the story immediately. So the key takeaway here is that visualization isn't about making things pretty. It's about encoding information in ways that can leverage how human perception actually works. And also, an important design principle here is we should always use as much precision as your decision requires and no more. extra precision can always distract from the insight. Before we go further, let's establish a common vocabulary. This example scatter plot showing female life expectancy by the percentage of urban population has all the standard components that we will encounter. At the top, we have the title, and this tells viewers immediately what they are looking at. So never skip the title. It's your visualization's headline. And then we have those data marks, and these are the colored circles here on this plot. These are the actual visual representation of our data points. Each circle here is a country, and it's positioned according to two measures. So the first measure is the percentage of urban population, and second measure is a female life expectancy. On each axis, we can see those marks and those axis titles and axis labels. And in addition, we also have tick marks, and these are those small lines along the axis that help us read the value precisely. And sometimes we also have the grid line. These are these vented horizontal lines and vertical lines crossing the plot area. They help our eyes trace from a point to its value on each axis. And in the lower right, we also have the legend. And this tells us what color represents. So Africa, Asia, Europe, Middle East, and so on and so forth. And you can also notice that the size of the circle varies. And that's encoding yet another example. The simple visualization is actually showing us the relationship between four variables simultaneously: the urban population percentage, the life expectancy, the different regions, and also the population size. So understanding these components will help us to concretely understand data visualization, and we can now critically evaluate them. Now, here is something that may surprise some people. Formatted text and tables can also be data visualization. Look at the example here on the left, showing the number directly. The before shows two cluttered pie charts comparing survey results. The after, just one big bold number, 68% of kids expressed interest in science after the pilot program, compared to 44 before. So sometimes the most powerful visualization is just a single number, formatted to stand out. Also, the word cloud in the upper right shows search frequency. Bigger words represent more common searches like YouTube, State, Wikipedia. This jumps out because the size encodes importance. And also, when we look at table on the lower right showing average blood alcohol, notice that the bar here are embedded right in the table cells. The numbers are there for precision, but the visual bars let us compare at a glance. So the lesson here is that let's not assume visualization always means elaborate charts. Though sometimes even a strategic use of font size tells you a story more effectively than any fancy graphs. So visualization can be a simple sentence that states an insight clearly, or a well-formatted number, or a simple table. You've heard the phrase, a picture is worth 1,000 words. In data visualization, this isn't just poetry, it's literal truth. Let me explain why. So first, visualization summarizes large amount of data into a small number of visual elements. Imagine trying to understand the cell performance of 10,000 transactions by reading a spreadsheet. Now imagine seeing those same 10,000 transactions as a single trend line. So which one gives you insights faster? Obviously, it's a line. Second, visualization can reveal subtle details buried in crowded data. So the patterns that would be invisible in rows of numbers will suddenly jump out when you plot them visually. Third, visualization can capture hidden relationships. Two variables may be correlated in ways you would never notice from tables, but a scatter plot makes it very obvious. Additionally, visualization exposes trends and patterns. Is there something wrong, shrinking, increasing? A well-designed chart will answer those questions. And also, visualization amplifies your message. When you are presenting to the executives, a powerful visualization will help you convince them much better than pages of analysis. And finally, visualization help you tell story and facilitate communication. Data without a narrative is easy to forget, but data presented as a visual story is more memorable. That's also more persuasive and more actionable. Now let's show you some historical examples that prove just how powerful visualization can be. The first example is disease control with data visualization. And this is perhaps the most famous example of data visualization in history. And it happened in 1854. At the time, London was suffering a devastating cholera outbreak. People were dying by the hundreds, and nobody knew why. The prevailing theory was that cholera spread through bad air. But Dr. John Snow wasn't buying it. He had a conjecture that contaminated water was the cause. But how do you prove it? So Dr. Snow did something revolutionary. He mapped the data. So look at this visualization. Each black bar represents cholera deaths at that address. And John Snow literally walked the streets of London, recording where people died and plotted each case as a dot on the map. And what emerged? A pattern. The deaths weren't random. They clustered dramatically around one location, the Broad Street water pump. So this visualization didn't just reveal a pattern, it solved a mystery. Dr. Snow presented his map to local authorities. They shut down the pump and the outbreak stopped. So think about what happened here. The same data existed before Snow's map, the death records, addresses, all of it. But nobody could see the connection until it was visualized spatially. This is the power of right visualization. It doesn't change the data. It changes what you can perceive about the data. Snow's dot map is considered one of the founding moments of epidemiology and data visualization. If John Snow's cholera map is one of the most important visualizations in history, this one by Charles Maynard might be the most beautiful. So this simple image tells the devastating story of Napoleon 1812 invasion of Russia, and does so using 6 variables simultaneously. The time band flowing from the left to the right, showing Napoleon's army advancing towards Moscow. The width of the band represents the number of soldiers. See how it started thick on the left? That's 422,000 men beginning the march. Watching it narrow down as you move right toward Moscow. Soldiers dying from combat disease, starvation. By the time they reach Moscow, the mighty army has shrunk dramatically. And then the black band shows the retreat. Notice how narrow it even becomes. You can see the army essentially collapsed. Now look at the bottom of the chart. The line shows temperature. As the army retreated, temperature plummeted to minus 30 degrees Celsius. You can literally see the correlation between the falling temperature and the falling army size. So this single image encodes the army's geographic path, the direction of the movement, the army size at each point, the temperature at different point during the retreat, the time, and also the geographic location, the rivers, the cities, so on. So why does this matter for you as business professionals? Because this example shows that complex multivariate stories can be told in a single comprehensible image, and provided that if you choose the right encoding. So your quarterly business review might not involve frozen Russian rivers, but the principle is the same. Use visual encoding to make a complex relationship clear. Now let's look at how visualization can reveal patterns that would be invisible in raw numbers. This comes from Christian Roberts' book. The question is, what age of men do women find most attractive? Look at the left column. It shows the women's age, 20, 21, 22, all the way to age 50. And next to it, the red number shows the age of the men that women found most attractive. At the first glance, it looks just like a list of numbers. But look at the visualization on the right, where those same numbers are plotted spatially. So now you can see the relationship. The dotted line shows where women would rate men their own age as most attractive. That would be age equal age line. The actual data, women consistently find men close to their own age most attractive. A 20-year-old finds 23-year-old most attractive, a 30-year-old found a 31, and a 50-year-old prefers 46. The data points track pretty close to the diagonal line, suggesting women's preferences age along with them. Without visualization, this pattern would require careful statistical analysis to detect. With the visualization, it jumps off the page in seconds. Here's where it gets very interesting. Visualization becomes even more powerful when you use it for comparison. On the left, we have the same data we just saw, women's age versus the age of the men that find most attractive. Now, let's look at the right side. That is the male version. A man's age versus the age of women he finds most attractive. Do you see the dramatic difference? For men, regardless of their age, the most attractive women are consistently in their early 20s. A 20-year-old man finds 20-year-old women most attractive. No surprise. But 30-year-old man, still 20, a 40-year-old, still 20, and a 50-year-old man, still early 20s. The male data points don't follow the diagonal at all. They form a flat line. Now we are not here to make a social commentary, but look at what visualization accomplished. By placing these two charts side by side, a profound difference in behaviors become instantly apparent. If I gave you two spreadsheets with these numbers, would you have spotted this pattern? Maybe, with careful analysis. But with visualization and a comparison, the insight is immediate and undeniable. So this is why comparison is one of the most powerful techniques in visualization. The context changes everything. Here is another example, and this is a story told with data visualization. This story is from Wall Street Journal. This example from Wall Street Journal demonstrates visualization as storytelling. It is an article, and it's very interesting and interactive piece documenting a year of suicide bombing worldwide. So each circle here represents an attack, and the size indicate the severity. And as you scroll down, you see more and more story unfold. So for example, on this image, the circle represents attack, the size of the circle represents the severity, and the color indicate which organization was responsible. So what makes this very powerful isn't just the data display, it's how it was presented. The article scrolls through the data, progressively reveal the patterns, which organizations were responsible, where attacks concentrated, and how frequently change over time. So a visualization doesn't have to be a single chart. A visual story is a sequence of visualization that build on one another. Same marks, same visual language, different encodings. It's like chapter in a book. Each one adds a context. And this is data visualization as journalism, as storytelling, as communication. It informs and it moves people. Now let's step back and recognize that not all visualizations serve the same purpose. There are fundamentally two types. Presentation visualization is about communication and persuasion. You've done your analysis, you found your insight, and now you need to convince others. The author, that's you, plays the dominant role. You are crafting a specific message. The audience here is relatively passive. they're receiving your story. Exploratory visualization is different. Here, the purpose is to answer questions or discover insights you don't yet have. The authors provide tools, interactive dashboards, filter reviews, and the audience here takes an active role exploring the data to answer their own questions. Both types are very valuable and they serve different purposes, and they require different design approaches. Presentation visualization should be polished, focused, and stripped of everything that does not support your message. Exploratory visualization should be flexible, comprehensive, and enhance discovery. Now let's talk about the type of data with data visualization. Every visualization fundamentally involves two types of data, measures and dimensions. That's it. Measures answer the question how much or how many. Dimension answers the question of what. Look at this bar chart. On the y-axis, we have regions, west, east, central, south. These labels tell us what we are looking at. These are categories. In visualization terminology, we call these dimensions. Then on the x-axis, we have sales ranging from 0 to 700,000. This tells us how much, and we call these measures. The dimensions answers what or which, what region, which product, which customer segment. Measures answers how much or how many, how much revenue, how many customers, what percentage. These are the numbers that we can add, average, and aggregate. So measures are numbers, and these are numerical values we care about. In the suicide bombing story we saw earlier, the measures include the number of attacks, number of people killed, number of attackers. These are all quantities, things that you can count, sum, or average. So here's a question for you. If we're evaluating student performance in a class, what are the measures? Think about it. These can include exam scores, assignment grades, attendance counts, hours spent on studying, and so on and so forth. So notice that here, the measures are typically the things that mathematical operations make sense. You can calculate the average exam score. You can sum the total absence. Measures are what you typically want to aggregate and analyze. Now let's understand dimension. Dimensions provide the context for measures. They answer questions like who, where, when, which category. So in the suicide bombing example, the dimensions included attack location, terrorist organization responsible, attack target, gender of the suicide bombers. All of these are categories or ways of grouping or segmenting the data. So back to our student performance example, what would dimension be? The gender, the major, the year of the study, and then geographic location. All these would be examples. So dimensions are your slicing and dicing tools. They let you break data into meaningful groups. And here's the relationship. You typically aggregate measures across dimensions. So average score by major, total sales by region, count of students by class year. So measures give us the number, dimensions give us the structure for analysis. Before we can visualize, you need to properly prepare the data. Visualization tools are not magic. Before data can be visualized effectively, it must be integrated, cleaned, structured, and in tabular form. Each row must represent the same type of analysis object. Each column must be an attribute of that object. If you bring messy, poorly structured data into a visualization tool, you will get a messy visualization. So data preparation can happen outside your visualization tool or inside it. Either way, clean, structured data is the foundation of good visualization. Now let's talk about the kind of information people actually want from the data. For individual variables, with dimensions, you can see what categories exist, what regions do people operate in, what product category do we sell. With measures, you can understand the distribution, center, spread, shade, outliers. What is the total order size? How much variations exist? If you have two variables, things get more interesting. If you have two measures, You can look at the correlation. Are they linearly correlated or are they not correlated at all? If you have one dimension and one measure, now you can compare, you can rank and show the trends over time, or you can reveal composition. If you have two dimensions, you can look at hierarchy, like regions within countries or products within categories. For more than two variables, the deeper relationships can emerge. Modern visualization tools make it very easy to show 3, 4, or even more variables simultaneously. But here's an important warning. You need to be careful about adding more than 3 or 4 variables to a single visualization. More is not always better. At some point, you create confusion instead of clarity. Cognitive overload defeats the purpose of visualization. The goal here is insight, not complexity. Sometimes the most powerful visualization is the simplest one. Let me also quickly clarify some terminology that may cause confusion down the road. So you will see viz, or visualization. Viz with Z is a single chart, graph, table, or text element. It's one discrete visual element. Visualization often refers to the broader and more abstract term. It can be a single viz, a dashboard made of multiple vizes, or a story that organizes dashboards and vizes. So when people say create a viz, they usually mean create one chart. When they say build visualization, it typically means a more complete dashboard or story. But don't get hung up on terminology. The industry isn't perfectly consistent, but having some shared vocabulary helps us communicate more clearly. Now let's walk through the major types of data visualization and understand what each one does the best. Starting with histograms. Histograms are ideal for understanding the distribution of a single measure. They answer questions like, what values are most common? Is the distribution skewed or symmetric? Are there multiple peaks? Are there gaps or anomalies? In this example, we see employee ages. Notice how much information is packed into one single chart. We see a concentration of very young workers, and then we see another peak among mid-age workers. But then we have a suspiciously low number of employees in their early 30s. So that gap alone raises managerial questions. So think of the histogram as X-ray. It shows you the internal structure of the data that you couldn't see by just looking at averages. The average age might look fine, but the histogram reveals there is actually a concerning gap in mid-career employees. So questions the histogram can answer: what is a typical value? How spread out is the data? Is the distribution symmetric or skewed? Are there multiple peaks? Are there outliers? Then moving to box plot. The box plot are also called a box and a whisker plot. This is another powerful tool for understanding distribution, especially when you want to compare multiple groups. So let me decode this for you. The box in the middle represents the mid 50% of the data from the lower 25 percentile, first quartile, to the third quartile, which is 75% quartile. And this is called interquartile range. The line inside the box is the median. And then the whiskers extending to the top and the bottom show the rest of the data. And this typically extends to 1.5 times the interquartile range, or to the actual minimum and maximum values. The dots above the whiskers are outliers. These are the values that are unusually high or low compared to the rest of the data. So box plots give us 5 summary statistics in one glance: the minimum, the first quartile, the median, the third quartile, the maximum, and plus they also flag outliers. So now watch what happens when you compare box plots with dimensions to tell a more complex story. So this example shows salary distribution, but broken down by 2 dimensions: gender, female in orange, and male in blue. Also by pay grade, 1 through 5. So each vertical pair compares the salary distribution for men and women at the same pay grade. The shaded region in the background shows the prescribed salary range. So what story can we tell from here? So at pay grade 2, we see significant similarity in the boxes. So which means men and women earn similar salaries. But then if you move up or move down the pay grade, then something troubling emerge. There's clear separation. Women's median salary is much lower than men's at the same pay grade. This single visualization reveals gender pay disparity in a way that no table of numbers could match. The pattern is immediate, visual, and prominent. This is what makes visualization powerful for advocacy and persuasion. The same data in a spreadsheet may be dismissed or overlooked, but visualized this way, it demands attention. Line chart. When time is one of your dimensions, the line chart is almost always your best choice. So this simple line chart shows a sales trend over 1 year from January to December. The line connects monthly data points, and our eye naturally follow it to perceive the pattern. So what does a time series reveal? The trend. Is it going up or down or flat overall? So here, despite the month-to-month fluctuation, we see the trend is clearly upward. Sales are growing. It also shows seasonality. Are there predictable patterns? Looking at those red arrows making up and downs, the sales seem to dip in certain months and then rise in others. It also reveals anomalies, so any unusual spikes or drops. If March sales suddenly crashed, it will be very obvious on a line chart. So the lines connect and they emphasize continuity and flow. Your eyes follow the line and perceive the journey over time. When you add another dimension to a time series, you get multiple lines, one for each category. So this chart shows internet usage by region from year 2000 to year 2012. Each color line represents a different region. Europe, America, Asia, and others. So we can compare trends across different categories. You can see Europe started ahead and stayed ahead. Then America showed steady growth. And Asia started very slow but grows steadily. With multiple lines, you can answer questions like, who is growing fastest? Who is catching up? Are the gaps widening or narrowing? Did any region experience unusual patterns? A word of caution here, you don't want to put too many lines on one chart. When lines start to cross and tangle, comparison becomes very difficult. So 5 to 7 lines is usually the practical maximum for readability. Bar chart. When we want to compare the ranking, then horizontal bar charts are the best choice. So this example, which is a horizontal bar chart, ranks countries by the percentage of GDP spent on healthcare. So why do we want horizontal bar chart for ranking? So first of all, comparison is easy. Our brains are very good at comparing the lengths. So longer bars means higher value. And this is very clear. Second, horizontal bars accommodate long labels. So country names can be very lengthy. So for example, Marshall Islands. If you put this in a vertical bar, if you try to fit Marshall Island on a vertical bar, it becomes a mess. And then horizontal bars also enable quick top to bottom scanning. Your eyes naturally scan down and the ranking order is obvious. Also, notice that the arrow highlighting some interesting patterns here. So Marshall Island and the United States are both at the top. But then the third one, which is Sierra Leone, it's a poor country, but also ranks pretty top. And then you can see there the next one has a significant gap. So this tells us something very interesting. So high healthcare spending doesn't necessarily correlate with wealth. Then talking about vertical bars. These are also called column charts. They are best for comparing categories, especially when you are not emphasizing ranking. So comparing values across category is something humans do very well when the length is involved. So this bar compares GDP across regions in 2012. America is the highest, followed by Europe and Asia, and then Middle East. So column charts and bar charts are essentially the same tool. They are just rotated by 90 degrees. The choice often comes down to label length and what feels more natural for your specific comparison. The pie chart. And pie charts are possibly the most controversial visualization in existence. Pie charts shows part to whole relationship. So how categories contribute to a total. Here we see carbon dioxide emission by regions in 2000. So why pie charts are controversial? This is because humans are bad at comparing angles and arc lengths. So look at Asia versus America. Can you tell which one is bigger by just looking at this pie? I certainly cannot. Without the labels, I would just be guessing. The numbers are so close. The sizes are also very close. So if we compare the pie chart to the bar chart that we have the bar length comparison is something much easier for human eyes. But angle comparison, not so easy. So when should you use pie charts? You can use them when you have very few categories. So for example, 2 to 4. And if the differences are very large and very obvious, and then you specifically want to emphasize the part to whole relationship. In that case, use a pie chart. You should not use a pie chart when you have more than 4 categories, when your slices are pretty similar in size, and also you need precise comparison. If you ask me, my honest advice is that never use pie chart. When you have something to compare, use a bar chart instead. But if your client loves pie charts and you are showing 3 categories with dramatic differences, they are acceptable. Another chart, which is less popular, is called Waterfall chart. A waterfall chart is specialized variation of a bar chart. It's particularly useful when you want to show how individual components add up or subtract from a total. So it's a combination of pie chart and bar chart. On my example, this shows the same carbon dioxide emission data by the region. Each segment float at the level where the previous one ended, and then they build up to the grand total 100%. So why is this better than a pie? First, you're comparing length of the bar now, and this is much easier for human visual system. Second, you can see both the individual contribution and the running total as you go up. Third, the percentage can sit right on top of each bar without cluttering. So waterfall charts are especially powerful for financial presentations, showing how revenues minus various costs arrive at profit, for example. Each bar can show addition or subtraction, and you see the cumulative effect. When you have 2 measures, then scatter plot is an essential tool. This example plots the average outbound tourism in terms of spending against the inbound tourism spending for Asian countries. Each dot here represents a country. The trend line here shows a general relationship as outbound spending versus inbound spending. So as you can see, as outbound spending increases, the inbound spending also tend to increase too. And there is a positive correlation. So a scatter plot can reveal multiple items here. The direction of the relationship. So do the variables move together or do they move in opposite direction? It also shows the strength of the relationship. How tightly do the points cluster around the trend line? If they are tight, that means strong correlation. So here we can see the considerable scatter. This suggests the relationship is moderate. We can also show outliers on scatter plot. So these are any points far away from the pattern. You can also see the shape. Is the relationship linear or curved? The current one is pretty linear. But the scatter plot can also reveal nonlinear relationships too. Always remember, correlation here doesn't mean causation. Even if outbound and inbound tourisms are correlated, the scatter plot doesn't tell us why. When we add more variables to a scatter plot, for example, size and color, then we get a bubble chart. This example chart compares China, the red dots, and United States, which are the blue dots, on tourism metrics over multiple years. Again, the tourism inbound spending versus tourism outbound spending. We can see that US consistently has higher inbound tourism, so receiving more tourists, and also higher outbound tourism, citizens traveling abroad. The US cluster is in the upper right corner, and China cluster is on the lower left. We also see that China's bubbles from different years show a movement rightward, increasing inbound tourism over time. The size reveals the population. So you can see China's bubbles are much bigger. This single visualization let us compare two countries across two tourism metrics while also showing time progression and population context. The power here is real, but so is the danger. Every added variable increases the cognitive load, so you need to design very carefully. Tree maps are fantastic for showing hierarchical data with multiple variables, especially when you want to see how parts nest within a whole. This example shows the US stock market from yesterday. The entire rectangle represents this whole market. Within it, we see major rectangles. These represent sectors, for example, information technology, hardware, healthcare, so on and so forth. Then within each sector, we see smaller rectangles represent subsectors, for example, software, semiconductor. And then within them, we see individual company rectangles. The size here encodes the market capitalization. Bigger rectangles means bigger companies. So look at Nvidia, Microsoft, Amazon, Google. These are big companies. The colors encode daily price change. Green means the stock is up. Red means it's down. The intensity shows the magnitude. So what can we learn at a glance? We can see that Nvidia increased, Microsoft increased, but Amazon had a bad day. It was down by a big red rectangle. So this is hierarchical information. The market contains sectors, sector contains subsectors, subsectors contain companies. A tree map lets you see the hierarchy while also comparing sizes and additional variables, for example, price change through color. Something similar is called heat map. A heat map uses color intensity to highlight patterns across dimensions. On my slides, this is a map shows percent change in country population from 2010 to 2020. Every county in the US is colored based on its population change. You can see that the West Coast, especially around major cities, showing strong growth, the dark colors, teal colors. But in the meantime, we can see the Midwest and also Appalachia area shows orange, which means population decline in those regions. So this geographic heat map tells us a story about American demographic shifts that would be impossible to perceive from a table of 3,000 county statistics. So heat map work because we are good at perceiving color gradients, hot versus cold, intense versus pale. These differences register immediately with human eyes. You can use heat map when you have geographic data that benefits from spatial layout, and when you want to highlight patterns across a grid or matrix, if you color intensity meaningfully represent your measure. How to choose appropriate chart to use? I will leave you with this final idea. There's no universally best chart. The best chart is the one that answers your specific analytical question with the least cognitive effort. You should always start in the center with the question, what would you like to show? And then you choose the visualization. If you want to do comparison, choose bar charts, column charts, line charts. If you want to show relationship, scatter plots for 2 variables, bubble charts for 3 or more. If you want to show distribution, then histograms for a few data points, line histograms or scatter plot. If you want to show composition, if it's changing over time, using stacked charts. If it's static, then use pie charts or waterfall charts or just stacked bars. I encourage you to bookmark this reference. When you are starting a visualization, ask yourself, what am I trying to show? And then you follow the appropriate path. But remember, this is a starting point, not a rule book. Sometimes unconventional choices work brilliantly. Sometimes the conventional choices is exactly right. The link at the bottom goes to an interactive website. Let's bring it all together. Data visualization is not about making pretty pictures. It's about encoding information in ways that leverage how human perception works, so that patterns, relationships, and insights become visible and compelling to human eyes. In this video, we covered the data triad and where visualization fits. We saw historical examples proving visualization's power to reveal hidden truths. We also learned the difference between measures and dimensions. We also walked through the major chart types and what each does best. So here's what I want you to take away. Match your chart to your question. What are you trying to show? Comparison, distribution, relationships, or composition? Less is often more. Don't try to add complexity for its own sake. The best visualization is often the simplest one that reveals your insight. And last, visualization is translation. You're translating data into a visual language that human can process quickly and accurately. In our upcoming session, we will put these principles into practice using data visualization tools. We will learn not just the theory, but hands-on skills to create compelling visualization ourselves. So thank you for watching. I will see you in the next video.